Okay, let's look at f of x equal x squared divided by x squared minus 1. First, for the x-intercepts, well, the x-intercepts occur when f of x is equal to 0, and f of x is equal to 0 when the numerator is 0. See, the numerator is x squared, and the numerator is 0 when x squared equals 0 or when x is equal to 0. We also have a denominator. We have a rational function here, and this denominator is equal to x squared minus 1. Now that's 0 when x is equal to 1 and when x is equal to minus 1. So this is where the vertical asymptotes will occur. Vertical asymptotes occur when the denominator is 0. So we have x-intercept 0, 0, and this is also the y-intercept. And we have x equal 1, x equal minus 1. We have these are the vertical asymptotes. Okay. Now let's look at the end behavior. So we have the limit as x goes to infinity of x squared over x squared minus 1. And we just have to pick off the lead terms. The leading terms would be x squared in the numerator and x squared in the denominator. So we're looking at the limit as x goes to infinity of x squared over x squared, which is equal to 1. And in fact, this is the limit as x goes to minus infinity as well. So in this case, this is plus infinity and minus infinity. So the end behavior levels off at y equal 1. So in fact, this is y equal 1 is a horizontal asymptote. Okay, so that's what we get here. Y equal 1, a horizontal asymptote. Okay, now let's go on to f prime of x. Okay, taking the derivative, we use the quotient rule here. In the denominator we have x squared minus 1 squared, and here we have x squared minus 1 times the derivative of the numerator, derivative of x squared, that's 2x, minus the derivative of x squared minus 1, which is 2x, times the numerator x squared. And if we simplify this numerator over here, we come down to minus 2x, because here we have x squared times 2x is 2x cubed, and over here we have a minus 2x cubed if we multiply these out, so those cancel. This 2x cubed minus 2x cubed, and we're just left with this minus 1 times 2x, so we're left with the minus 2x in the numerator. Now this is 0. F prime is 0 when the numerator is 0. That's when x equals 0. So when we do our plus minus analysis of f prime, we put on the number line the zeros of the numerator and denominator. Okay, so that would be plus or minus 1 for the zeros of the denominator, and x equals 0 for the numerator. Okay, so here we have 0, and I'll put an open dot at minus 1 and an open dot at 1 because the function doesn't exist there. Those are vertical asymptotes. So in fact, here we can remember that by putting dotted line here and a dotted line here. Okay, now if we go to the right of 1, we're going to substitute into this. Notice the denominator is squared, so it's always positive, so we really only have to substitute into the numerator. So to the right of 1 for x equal 2, for example, the numerator is negative, so this is negative. If we substitute something like 1/2, again, negative numerator. And to the left of 0, if we substitute a negative value, this will be positive. Okay, and that's true here and here as well. So on this side, the function is increasing to the left of 0, and to the right of 0, the function is decreasing. Okay. All right. Let's look at the second derivative. So we're going to do a quotient rule. So first we're going to square this denominator. We have x squared minus 1 to the 4th. And then we put x squared minus 1 squared here. Put the denominator here times the derivative of the numerator, which is minus 2. Minus the derivative of the denominator. Here we do a chain rule, bring down the 2, x squared minus 1 to the 1, times the derivative of x squared minus 1 times 2x, times the numerator here, which is a minus 2x. Alright, now what we can do is cancel out x squared minus 1 from each term in the numerator. From here, cancel out one of these and cancel out this one. So if we do that, we have in the denominator we have x squared minus 1 cubed here. This goes down to exponent 1. So here we have x squared minus 1 times minus 2 times, okay, this x squared minus 1 cancels, so we have times 2x times minus 2x. And this simplifies, okay, and we get 6x squared plus 2 divided by x squared minus 1 cubed. Alright, so let's do a plus minus analysis on that. Notice that the numerator is never 0. This is a positive quantity plus 2, so that's never 0. That's always, in fact, that'll always be bigger than or equal to 2. So if we do our analysis, we have to put the zeros of the numerator and denominator on the number line. So the numerator does not have any zeros. The denominator contributes plus 1 and minus 1. And those are both open circles because f does not exist. The function does not exist at those values, minus 1 and 1. In fact, those are vertical asymptotes. Okay, now the exponent here is odd. Alright, so this is not always positive. Like in the case of f prime, the denominator had an exponent of 2 in that case. Alright, so let's substitute in something bigger than 1, like 2 for example, and here we have 4 minus 1, which is a positive number cubed. Okay, so that's positive. Here we'll substitute in 0, and we get 2 on top, and we have a minus 1 cubed, which is negative. And substitute in minus 2, top is positive, and in the denominator we have 4 minus 1 cubed, that's positive. Alright, so we have our function, our f is concave up here, concave down between minus 1 and 1, and concave up to the right of 1. Okay, so now let's using the information that we have, let's draw a function. Oh, these are inflection points at minus 1, oh sorry, no, these are not inflection points because these are asymptotes. So we have no inflection points. Let's write that down. We have no inflection. What about max-mins? What do we have here? I don't think I mentioned that this is a maximum. Here the function is going up and down, so 0, 0 is a maximum point. That's a max. Okay, so let's put in some of the information that we have into a graph. And here's what we have. Okay, so we have our intercept 0, 0, which is also a maximum. We have 1 and minus 1 vertical asymptotes. We have y equal 1, which is a horizontal asymptote. That was the end behavior. Okay, now the function is concave down between minus 1 and 1. It's concave down. So here, if we look at these asymptotes, since it's concave down here and here, this must be going down to minus infinity, to the left of 1 and down to minus infinity, to the right of minus 1. This is confirmed by the fact that we said that if you look at the increasing decreasing chart, we said the function is decreasing here, here, and here. Let's see that we have that. Well, yeah, the function is decreasing here. Okay, and here the function should be increasing to the right of 0, and that's what we have. It is increasing here. Okay, now to the right of 1, we're concave up, plus our function is decreasing. So the only choice here is that we must be going up to infinity on this side of the vertical asymptote, because as we go from the left to the right, we are decreasing. And then here's our end behavior. We're going to level off at y equal 1. And this is also concave up. Alright, and here we're also, on the other side, we're also concave up. And let's see, our function should be increasing in that interval as well. Let's just check that. Yeah, it's increasing here. So the only way to draw that would be like this. And that's our picture. That's our picture of f of x.